We've defined pH as a means of getting the strength of acids. We're now going to go to a related quantity, pOH, that relates to the strength of bases. So our learning goals for this video will be first to define what pOH is, and then to define the relationship between pOH and pH, because this will turn out to be very important in aqueous solutions. Let's start by considering a solution where the hydroxide ion concentration is 1 times 10 to the minus 2 molar, or 0.01. We're going to define pOH just as we did for pH, where we have hydroxide ion concentration is formally defined as 10 to the minus pOH power. So what that means in effect is that the hydroxide ion concentration, if it's 1 times 10 to the minus 2 molar, then it will also be equal to 10 to the minus pOH, and pOH is equal to 2. Like pH, if we have a small pOH, we'll have a large hydroxide ion concentration, and if we have a large pOH, we're going to have a small hydroxide ion concentration. So we have to think backwards a little bit because of the definition, including a minus sign. Now it turns out we can find pOH if we know the pH of a solution, but that's only true if it's in water, because we have this very important relationship between the two that comes from the water autoionization equilibrium. Remember, that's when two waters come together and they dissociate to form a hydronium ion and a hydroxide ion. And it has an equilibrium constant of 1 times 10 to the minus 14. Now, this always happens in any water solution, and it means that this is always going to be true when we're in water, that the hydronium ion concentration times the hydroxide ion concentration is going to equal to 10 to the minus 14. So if we're in water, this relationship is always going to be true. Now let's suppose we have an aqueous solution where we have the pH of 2. What can we say about the pOH? Well, first of all, let's unravel what pH 2 means. Well, the hydronium ion concentration is equal to 10 to the minus pH, and that's equal to 10 to the minus 2. So that means that we can plug it into this relationship between the hydroxide ion and the hydronium ion concentration in any water solution and say that 10 to the minus 2 times the hydroxide ion concentration is equal to 10 to the minus 14. All we've done is take our concentration of hydronium ion and plug it into that formula that comes from the equilibrium of the autoionization of water. Now when we do this, we can solve for the hydroxide ion concentration. It's just going to be 10 to the minus 14 divided by 10 to the minus 2. And if we do our math correctly, we should come up with 10 to the minus 12. So our hydroxide ion concentration now is going to be equal to 10 to the minus 12 molar, and we can read directly off of that exponent to find out that the pOH is equal to 12. See, it's not very difficult at all. I want to flip the script though now and consider a solution where we know the pOH and we want to know what the pH is. We're going to follow a very similar procedure. We start with a hydroxide ion concentration, which is equal to 10 to the minus pOH power, and that's going to be 10 to the minus 8 because we're given that pOH is equal to 8. So now when we plug that into this relationship between the hydronium ion concentration and the hydroxide ion concentration, we have the hydronium ion concentration times 10 to the minus 8 is equal to 10 to the minus 14. So now we can again solve for the hydronium ion concentration. It's going to be 10 to the minus 14 divided by 10 to the minus 8, and that gives us 10 to the minus 6. Once again, we can read right off the exponent to get the pH, and that's going to be 6. So these kinds of problems are not very difficult if you know how to handle both pH and pOH, and we want to be able to interconvert between the two as much as possible. There's a special relationship that these examples have revealed. Let's take a look at that. The results of these examples were, in the first case, I had pH plus pOH was equal to 2 plus 12, which is equal to 14. In the second example, I was given the pOH and asked to find the pH, and in that case, the sum of the two was 6 plus 8, which also is equal to 14. So we might ask, is this always true? Well, let's consider that equilibrium that has Kw as its equilibrium constant. Kw is equal to the product of the hydronium ion concentration and the hydroxide ion concentration, and I said that it is always equal to 10 to the minus 14 when we're in an aqueous solution. So let's unwrap that in terms of pH and pOH. If I write the hydronium ion concentration as 10 to the minus pH, that's just the definition of pH, and I write the hydroxide ion concentration as 10 to the minus pOH, that's the definition of pOH, I can write this. Now I know that that's equal to 10 to the minus 14. So what is this telling us? Well, whenever we multiply two numbers where the same base is raised to an exponent, the product of those numbers is just the sum of the exponents. So in other words, negative pH minus pOH is equal to negative 14. Well, I can multiply through by minus 1, and I find that pH plus pOH is equal to 14. And this is always true in aqueous solutions. So if you can remember this simple relationship between the two, it makes it very easy to convert between pH and pOH and give you an idea of how to handle the strength of acids and the strength of bases at the same time.